Hey, hi everyone, good morning. Friends, can you hear me? Please confirm. Hello? Yeah. Hey, thank you, Enoch. Yeah, also please confirm if you are able to see my screen. Yeah, I'm assuming a few people have connected directly from YouTube. And yes, I'm just checking if you're able to see the screen and are you able to hear me? Please confirm, everyone. Okay, wonderful. Yeah, thank you. Okay, for people who are joining for the first time, this is me. Let me introduce myself. My name is Sharad Chandra. I am a director of Innodatatics, and of course, I also serve as trainer. And my core subjects are basically machine learning, deep learning, big data, and then the revolutionized Spark, Apache Spark tool. So I cater to these kind of tools and technologies. And I have overall 15 years of experience working with various domains in the space of analytics, blah, 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 blah. Right? So that is basically my introduction. Just to cut it short, let me directly jump to the subject. We are going to talk about this particular topic today, hypothesis testing. So, how many of you are familiar with hypothesis testing? Or we basically call it as confirmatory data analysis. It's called as confirmatory data analysis because you're making sure some of the assumptions, some of the conditions that you're getting are validated, right? You're making sure they are validated. So you're making some assumptions and you're testing them. And hence it is also called as hypothesis testing, right? Now, let me talk about a couple of examples and then we will come back to this mind map, which is hosted on our website, 360dgtmg.com/mindmap-data-science. But let us start with the discussion here. So I want to understand on how many of you actually understand the term hypothesis testing. Now, you might assume that I'm repeating. This is basically the last week, even when you might have attended. I have covered this particular part, but there are a few more people who wanted the session to be retelecasted, redone. So this is a retelecast of the previous week's session. We will be conducting the session today and tomorrow, the same time. So for people who have attended the last week, it is a repetition, but I request you people to, it's no harm in taking the revision, right? So yes, let's begin. So we're talking about hypothesis testing. Hypothesis basically means an assumption. Hypothesis means assumptions. We are making assumptions for a lot of things. Data science is all about estimating an unknown thing. We are doing estimations, right? When I say estimations, this is basically predictive analytics branch of your entire data science or data analytics field. Predictive analytics, pardon my handwriting, I'm really bad at it. Now, when you have to predict a value that you're not aware of, there are certain standards that we need to follow. It's science, basically. It's a science, it's an art, right? So let us try and understand how we make estimations. Now, let's say you have to make an assumption on what is the age. Okay, let me talk about this. Age of people who are basically getting killed with COVID-19, who are dying due to COVID-19. We don't know it is an ongoing event or it is a future event. It's still going on. So what I will do, I will have to collect the entire data, right? Collect the population data. When I say population, we are basically saying we are considering the entire data across the globe. And then we analyze what are the ages of the people. But there are multiple people, multiple ages. So I would want a representative value for estimating. So I will say average age of people who are dying due to COVID-19. So I will take the data, but can we collect the entire data of the population? Can we do that? It's not possible, right? We will not be able to get the complete population data. So what we do is we collect a sample data. We get only a sample data, right? On the sample data, let's call it as, let's say age, sample of age, and probably I'm collecting 75 years across the globe. I've randomly picked the numbers: 75 years, 60 years, 50 years, 52 probably, 80, 95. Kids are also dying due to COVID-19, so I will have 10, 20, probably 38, 80 again, 77, so on and so forth. I'm collecting, let's say, 100 values. I'm collecting the data for 100 people. These are all the people who died at their respective ages. So on this data, I would be doing average because that is what is required. I want to collect average age. So when I do this average, this becomes a sample average. So I'll have to represent it using X bar. Sample average, let's say it is 74 years. Assume, just for an assumption, okay? Calculated assumption, 74 years is the average age that we got. But this is only a sample average. It is a sample data average. So how can I generalize it for the entire population? Can I do that? Not really, right? Because if the same task is being done by, let's say, another agency, or for example, I am asking you, every one of you individually, to give me the stats. So each one of you would basically collect the sample data. And mind you, you are going to collect your own sample, right? There is no relation between each one of you. So individually, independently, you're collecting the samples. So this might be sample 1. The another person might collect sample 2, sample 3, sample 4. Irrespective of the sample size, okay, 100 value sample size, you people are collecting multiple samples. On the samples, You're basically calculating the averages. Now, among all these results, right, I don't basically have same results. These will vary. This is the problem when you are making an estimation for population using sample data. Okay? And then we have central limit theorem, which basically helps us to come up with confidence interval calculations, which basically says capture the variation of this data. So because there are so many variations and each one of this sample data that you're calculating is to reach this. We want to reach the population average, global average. But you are trying it using sample data. So everybody who's trying to do this challenge, take up this challenge, is basically trying to solve this problem. But there are certain variations that you are experiencing. So can I do average of all this, because it is a representative value? Average means representative value. So can I take all these averages and calculate average on top of it? I can do that, right? Average of averages. And that would basically be your population average. This is what central limit theorem basically helps us achieve. Right? So average of averages. Because this variation exists, we also have to bring in the confidence at which we are going to come up with this particular calculation. This is called as confidence interval. Sorry. This is called as confidence interval. We are saying we are predicting the result with certain confidence. And that confidence basically says that the result that we are getting, the actual result that we are getting, would always lie between this range for any one sample that you are calculating. And this one sample basically is called as, it is basically called as point estimation. It's called as point estimation. Okay? And using this point estimation, we basically calculate confidence interval. And the formula for confidence interval is given like this. We say point estimate plus, there is variation in this, right? You're calculating average, but each value is little different. So can I add that variation from this mu? Let's say your population average assumption is 65 years. Okay, assume. But when I try to calculate, I got 74 years here on one sample. That means there is a deviation here, right? That deviation can be explained as x bar minus mu. Right? This becomes your value that you are trying to check the deviation with population value. So you're basically saying 74 minus 65. So I'm getting 9. Right? So this variation is for one sample. If I do it with this sample, then there might be a different variation. If I take third sample, there might be a different variation. Right? So all these variations considered, I'm basically coming up with average variation. So let me write it here. I'm saying for one sample, this is the calculation. But for second sample, there might be another variation. Third sample, there might be another variation, so on and so forth. So you're saying point estimate plus this variation on a whole, all the samples considered together. That is called as margin of error. When you are calculating population mean, you would basically work with a single sample only. But on an average, what is the variation? If you can add that variation, then you are going closer to this particular calculation. This is the logic of inferential statistics. Inferential statistics basically means you want to make an estimation for population, and that calculation for population is called as parameter. Population parameter. But because we cannot get this, we are going to make statements for population parameter using sample statistics. But this sample statistics varies. Hence, we use confidence interval calculation to estimate the population, and the industrial standard for the confidence level is 95%. I'm assuming you all are familiar with these topics. If not, I would recommend you people to go through the videos that we have on our YouTube channel. This is the YouTube channel. There are basic statistics related topics. I would recommend everyone to go through these basic statistics videos. Okay, there are a lot of videos, just go through them. This gives you a basic idea about what is population parameter, what is sample statistic, why we need to make estimations, how do you make estimations, right? What does inferential statistics means, what does central limit theorem means, everything, right? All these things are explained here. Please go through them. All right. Now coming back now to hypothesis testing. Now we have understood the background of the approach for doing hypothesis testing or estimations. So hypothesis basically means assumption, and we are trying to test these assumptions. Okay, I'll take the questions in intervals. So let me finish this, and a half an hour break we will take the questions. Every half an hour break I'll take the questions. So assumptions, any business problem that you are given, right? We would generally make assumptions first, and we are trying to solve those assumptions. For example, I'll take the same case, average age of patients who are dying due to COVID-19. Due to COVID-19. So you're making some assumptions here, right? You're saying that old age people might die. How true is that? The assumption is, default assumption is old people are dying. How true is this? This is what we have to basically, right, comment or test. So the default assumption would always be, right, the current assumption, or I would say status quo condition. And we call this default assumption or the current assumption as null hypothesis. We call it as null hypothesis, which is represented as H0. Null hypothesis. The current one, current condition. Now, if this is wrong, when we are trying to prove, right, we basically have to prove that this is wrong. Your default assumption is this. But if this is wrong, we are always saying that hypothesis, null hypothesis is correct. That is the reason we are following that. But if this is wrong, then you have to also come up with an alternate option. right? That alternate hypothesis will be represented as HA, or we can also represent it as H1. And we call this as alternate hypothesis just by the name. The logic also says that this is the default one. But if this is not true, then there should be an alternate option, right? So that is alternate hypothesis. Okay, so this is the foundation of hypothesis state testing. So we first frame or make these assumptions, frame the statements. If you're solving any business problems, then first we do frame the statements. And this framing of the statements would be in line to the business problem that we are trying to solve. The business problem is always identified via the objectives and constraints. If you are able to understand this, then framing of the statements would not be difficult, because always your default or the current condition would be your null hypothesis, right? So let me take another example and explain this. We'll talk about this condition. There is a person who is walking on the road in MCU, right? Movement lockdown, basically movement control order, or in India we call that as lockdown. Let me take this sheet. So in the movement control order, MCO, or I would say lockdown, there is a person who is walking on the road. Okay. And this person has been arrested. Right? He was put behind the bars, jail. So what is the default assumption by the judicial system? Okay, irrespective of MCO or lockdown or any other external conditions, what is the default assumption of the judicial system? Across the globe, judicial system always assumes that the person who got arrested is only an accused. He is not a culprit. He did not do any crime. Unless until it is proven, he is innocent only. That is the default condition, right? So there is a person, right, who is put behind bars. This person is accused. And the default assumption is accused is innocent. Okay? We need to prove, we need to find evidences to basically say that no, he has committed the crime. Only then he will be punished. Otherwise, he will be released. That's the default assumption, right? So he will be released. So we need to find the evidence, right, saying that no, he has committed the crime. So that is basically the alternate hypothesis, which says no, he is a criminal. Whatever the crime it is, okay? Whatever the crime it is, we are saying alternate hypothesis says he is not an innocent. That means he is a criminal. Making sense, right? So this is how we frame the statements. But now we also have to evaluate these statements. Hypothesis testing is all about evaluating these conditions with evidence and sticking to one of those assumptions, one of those conditions. How do we evaluate? How do we evaluate this? So we need sample data and all that, right? So let's not get into sample data. I'm talking about a generic condition, generic scenario, right? I'll take this example. One person who was who's jailed, who's accused, we are assuming that by default is innocent, and the alternate hypothesis says no, he's a criminal. Okay? Till here, I'm assuming it is clear. But let me see if you have any questions. We'll continue after this. Let me take your questions if anyone has any questions. Okay. Yes, Hari. Yes. The default assumption, right? You're saying default assumption. It is your current condition. Depends on what business scenario you're dealing with. You would have that default condition as your null hypothesis. We are calling it as null. Null means the current condition. You're not doing anything different. Continue what you are doing. Okay, so that's basically one question I see here. Any other question, anyone? No? All right, let me move on. All right, so again, coming back to the discussion. We're assuming that one person who was put behind bars, who was accused, is produced in front of a judge. Right? There is a trial running and he is produced in a court of law. Okay? Now, what is the judge assumption? What does judge assume? Yeah, the judge assumption would always be that this person is innocent. Default assumption, right? This is what judge is assuming. And he wants to see if there is any evidence to prove that this is wrong. Okay? So there would be a discussion going on in the court of law, and lawyers try to fight the case and try to provide their evidences. Now we'll understand the cases. Okay, there are 4 cases that might arise. It's a 2 option, right? You have basically 2 categories, whether innocent or culprit. So let us assume that in reality, okay, first case, in reality, that person who was accused is actually innocent. In reality, he is innocent. He did not commit any crime. Right? So I'll basically draw this. I'll say H0 is true. In reality, right, we are assuming that this person has not committed any crime. So H0 is true. Now, when H0 is true, that means when the person did not commit crime, then he should be released, right? He should not be punished. He should not be punished. That means there is no evidence, assume there is no evidence to prove that he is culprit, then by default he will be released. So in the court of law, the lawyers have failed to reject the default condition. The judge failed to reject the default condition because there was no evidence. And because in reality he is innocent, this condition would be reality, true condition, the right decision, because judge is releasing that person, right? And this is termed as confidence. It is termed as confidence, which is represented as 1 minus alpha. 1 minus alpha. Let me rewrite that. I don't want people to get confused here. 1 minus alpha. Right? Now let's say, like it happens in the movies, there is some false evidence also created, right? Generally in movies it happens, right? There's false evidence produced in the court, and because of that evidence, the judge is rejecting the default condition. Now he has evidence to reject this default assumption. So he rejects null hypothesis. That means he's punishing, right? Rejecting null hypothesis means he has to go with alternate hypothesis. So he is punishing an innocent person, because in reality we are assuming he is innocent. Now this is a wrong decision, and this condition is called as type 1 error. It's an error and we call it as type 1 error, and this is represented as alpha. We'll discuss about alpha 1 minus alpha. This is alpha, which is basically an error. Now, the second case, let us assume the second case. In reality, let's say the person who was accused is actually a criminal. He did commit the crime. That means in this table, now it becomes HA being true. Alternate hypothesis is true. Now, if it is true, then he should be punished, right? If he is a criminal, he has to get punished. But in the court of law, again, like in movies, there is no evidence that is produced against this person. So what happens? What can judge do? He does not have any evidence to punish him, right? So he has to go with the default assumption, which says that he is innocent. But this is a wrong decision, because the culprit who was right, who basically did crime, has to be punished. But lack of evidence is letting that criminal release, and this condition is called as type 2 error, and this is represented using beta. And if there is an evidence, and if the person is criminal in reality, then judge would punish him, right? And this would actually be the correct action. The culprit should get punished, right? And this is basically called as power of the test, and this is represented as 1 minus beta. So what we are doing, we are generating the possible 4 conditions for these 2 decisions that we need to make. One of the decisions that we need to make. And we might get 2 right conditions. Let me mark them in the yellow. In the diagonal, you will have the 2 right decisions, and the other 2 options are the wrong options. You may go wrong as well. Okay? So we have to be careful basically on these conditions and choose the right decision based on data. So here data becomes very crucial. We estimate these calculations in this case of business scenarios. Now let me basically talk about, let me talk about the process of doing hypothesis testing. So like any other project, we all start with the business problem. We'll start with business problem. And we already know business problems can be explained using business objectives and constraints that we need to consider to solve those objectives and constraints for the business. Then we collect the data, sample data. Right? This is always sample data, and larger the sample data, better the inferences that we can make. Third is we pre-process or prepare the data, right? And then we perform the test. This test is nothing but statistical calculations. Statistical calculations are happening here. So this results in statistics. Using these results, we need to make, I'm writing it here, we need to make estimations. We have to make estimations for population. right? But we are estimating. Remember, we are not declaring, we are not gods. We are estimating on what might happen in the population scenario. And I'm again writing it here. Based on the results that we are getting, with some confidence, we make that inferences and we take those results, estimations, and based on this, we make conclusions or we take decisions. This is the flow that we have to follow. Okay? Hope everything is clear here. If you have any questions, as I said, please make a list of all those questions and we will basically break every half an hour and take the questions, right? All right. Let me move on. I'm erasing this. So we will basically discuss about hypothesis testing. We will look into the conditions on what test needs to be applied when. That is more important. And we'll see the examples also. We'll take a couple of examples in each case and try to solve the problem. So this is the table. Type 1 error, type 2 error. If I have to further explain type 1 error, we say type 1 error is a condition which occurs when you are rejecting a true null hypothesis condition. When it is true, you should go with it, but you are rejecting that true condition. That's type 1 error. If I have to write it for type 2 error, I'm writing it here. For type 2 error, we are saying, remember, we don't say accept, we say fail, because you're already in the null hypothesis condition, right? So you're failing to reject that condition. Fail to reject a false null hypothesis. Okay, remember this. If your null hypothesis is wrong, you have to basically reject it, but you don't have evidence to reject it. Right? Now always remember the names given for these conditions. Null hypothesis basically says continue what you are doing. So null hypothesis is known for the no action decisions that you are making. You say no action, or you say what is your default or current condition, and we call it as status quo. Whatever you are currently doing, continue doing it. It is good. Don't change the strategies. Don't change to something new. But if this default condition or current condition or no action condition that you're talking about, no action means not sitting idle, guys. No action means you're not doing something different. Okay? If this goes wrong, then you will have an alternate option for it. And here you say, to generalize it, you say take action. Do something different from what you are doing regularly. Right? So in this terminologies, if I have to explain type 1, type 2 error, type 1 error is called as a condition where you are taking action when it is not required. This is taking action, doing something different when it is not required. Let's say when not required. And type 2 error is exactly opposite to that. You're not taking action. You need to take action. Not taking action, you say when required. So you're punishing the innocent. You should actually release him, right? That is your default condition. You have to release the innocent, but you are punishing him, right? So taking action. In this type 2 error case, you should rather punish him, take action, But lack of evidence, you are releasing it. You're not taking action. Right? So that is the understanding between type 1 error and type 2 error. Alright. Let's look into a few examples. We'll do this in a little faster pace, and then we will look into the actual case studies using data we'll try to solve. And we'll understand, right, how the application, what is the mathematical intuition, how your inferential statistics confidence interval come to play here. So I'll start with this, a basic English statement. Our quality will not improve after consulting project. So we are doing consulting projects, right? If you're continuously doing the projects, your quality should improve, right? Any action that you're doing regularly, right? That action should be done more and more precisely, right? The quality of that action should be improved. But the management of the firm is a little worried, saying that, hey, no, if I do this particular project, I'm taking this consulting project, right? One particular project, it is not going to help me improve my quality. Maybe this was because, I'm just creating a story here. Maybe it is because the project that we are looking at here, this particular project, is not the project that you regularly do. Maybe, right? So this is, let's say, a project where you're saying website development. You are known for, let's say, solving business problem using machine learning. You have machine learning experts. But your client says, no, I also want website development. Please develop my website. So your management says that, hey, our quality is not going to improve. If I do this, I'm going to get a bad name because I'm not expert in that. So what are the assumptions that you make here? What is your default action? This projects. This is a new project. There is a question, right? There is a question to take an action. So we assume that no, the quality will not improve. No action. No action means no different action. So you're saying reject this website development project. You're not accepting, no action, right? Reject the website development, new project. When will you reject? When the quality is not improved. So we need to measure that. There should be a quantifiable value. We need to measure. Now, how do I measure it? Quality is a metric that can be basically coming from number of, the timelines, basically. It's a number of hours that you're taking to develop this, or number of features that you're going to give into the website, right? Or number of issues that are cropped up after you're developing this. So there is a different way to measure the quality. Assume we are taking the timelines. Assume. So if I am taking 30 days timelines, assume this is the default time. The client is giving 30 days time. So you're saying if you are able to complete the project without errors, of course, you are handing over the website within 30 days, then fine. But because it is not your work area, you are doubtful that it will not be completing in 30 days. So if on an average, I'm generalizing, guys, this is a generalizing statement that I'm making here. Hence, I'm using population parameter. If I'm taking greater than 30 days or greater than or equal to 30 days, then it doesn't make sense for me to accept the project. Right? No action. Equal to is also in null hypothesis only. 30 days, exactly 30 days, it's no good, right? It's not, it's like no profit, no loss scenario. You're just meeting the timelines. The client would, right, be having no positive impression or no negative impression. It is neutral. You are putting unnecessarily effort on something which is not your work area. So better you focus that time to another project, right, which is more relevant to you. Hence, equal to will always go in no action scenario. And if you take less than 30 days on an average for these kind of projects, then yes, you can accept the project. So we first understand the business problem, and based on the business problem, we see what is the default condition that we have and what should be the action that we need to take. We can understand these two, and then using some metrics, we measure and then decide whether to go with null hypothesis or reject that. This is how we do this hypothesis framing, statement framing. I'll take this as the second one now. The retail market will grow by 50% in the next 5 years. So this is 2020. So your business advisor is saying that by 2025, this X value, right? This is the revenue, assume. The market growth is measured as X% or X value. By 2025, you are saying it doubles. It grows by 50%. Right? Then you can imagine that it is doubling. That way. And the decision that you need to take now is, can I invest in retail market? Right? So null hypothesis and alternate hypothesis. There is an action in question. That is, should you invest in retail market or not? Always remember, null hypothesis is default action. That means currently you're working, let's say, in wholesale trading. You're not in the retail market. So continue what you're doing. No action. Always remember, no action. That means you're saying, do not invest. But when would you not invest? That's the question. And when would you take action, that is, invest in retail market? Because your financial advisor or your business advisors are saying retail market will grow by 50% or it is going to double in next 5 years. That means they have done their calculations. ROI calculations have been done, and they're suggesting this because you would get profits. So you're taking a decision saying that if on an average the growth is less than or equal to 50% of your X, whatever the current value is, then no action required. But if it is going to be greater than 50%, then take it. So you're coming with some metrics. This is how we frame the statement in this case. Another example. Our potential customers do not spend more than 60 minutes on the web every day. So I'm a director of Innodatatics and I want to do marketing of my product. We have automatic attendance and thermal tracking system product, which we have launched in the market. So I want to do more marketing. So I'm asking my marketing team to help me out. Innodatatics wants to market a product. So marketing team basically is brainstorming along with the management, and they're coming up with a statement that, hey, why don't we do digital marketing? Okay, let's say they're saying that let's do digital marketing, which is the regular thing nowadays. So this is a suggestion that your marketing team is giving. So why don't we put focus on marketing the product on social media, for example. So immediately, as a management personnel, I would ask, as a director of the company, I would ask, how much would I have to invest here? Right? That's the most important thing for me. So how much should I invest? And how much would I get in return? Would it be actually beneficial to the company or not? So marketing team says that, hey, there is a high chance that the customers are viewing now because everybody is digital due to lockdown. There's no point you're physically going and doing right traditional marketing. Let's do this. Then I'm asking her, what are the chances? What are the chances that it is actually going to be fruitful? So digital marketing team says that, see, there are good chances if our potential customers, right, are spending more than 60 minutes, then there's a good chance that they view our ad. I'm creating an entire story so that you understand the scenario, friends. So there's a good chance that the customers look at our ad if they are spending at least 60 minutes on the internet. Right? So now I would ask my data science team this question. Hey, data scientist team, can you find out whether our customers are actually spending that required time on it? Right? The assumptions that we are making is go with the traditional marketing only because it's investment that you're talking about. No action condition is always safe for me. Do the regular stuff. So I'm saying no action. Null hypothesis. But null hypothesis, no action would occur when your data scientist team finds an evidence that on an average, every day, the potential customers are not spending more than 60 minutes on the internet. In this case, there is no point doing digital marketing, right? So I would reject that idea. But if my data scientist team finds an average of greater than 60 minutes that our potential customers are spending on internet daily, then I'll say yes, go ahead. I'll give approval for doing the digital marketing. So what does data scientist team do here in the backend? They would do a survey, collect sample data. They do survey. They ask the potential customers randomly and they record the data. How many hours the potential customers would spend on the internet every day. One customer says I would spend 50 minutes. Some other customer says 120 minutes. Some customer says only 10 minutes, 30 minutes, right? Like that, we'll have different time that we collect. And then we do average of this. And then we estimate it using confidence interval, right? And then see whether the interval that I'm getting is actually holding the 60 minutes in it or not. Whether my customers are spending on an average close to 60 minutes or not. I mean 60 should be in this at industrial standard 95% confidence interval. If it is falling, then yes. Right? If this interval is greater than 60 minutes, then yes, jump with joy, you can go ahead and take action. Right? But if you are 60, that means if this interval is less than 60 minutes, if it is less than 60 minutes, then you go with no action. Right? So this is how we basically do the inferential statistics and come to a conclusions here. Next example. We will acquire 8,000 new customers if I open a store in this area. Right? So there is franchisee business and one of the franchisee personnel saying that, hey, we need to start a branch in XYZ location. And he's saying that the brand value increases because we are going to get 8,000 more customers. So as a management personnel, you are again checking, is the statement true or not? By default, you are saying, no, do not start the branch in that particular area. No action condition, right? So default action is you don't have a branch there, so you say no action. And then alternate hypothesis is state action. So again, you collect the sample data and you'll see whether the number of customers is less than or equal to 8,000. If yes, then null hypothesis. If it is greater than, then we will go with alternate hypothesis. Similarly, we do this. We will need 400 more person hours to finish this project in the timelines. So you basically, as a management, have to approve 400 person hours or not. So null hypothesis says if the project can be completed without these additional 400 person hours, then no action. Simple. You'll not give the approval to take more people. Alternate hypothesis, if it requires, yes, greater than 400 person hours, then yes, take action. Very easy statements, right? If you understand the business problems, making the statements are very easy. Less than 5% clients will default on their loans. Right? So a bank is going to the, let's say, the centralized bank. In India, we call it as Reserve Bank of India, right? So Reserve Bank, it's going to the bank, Reserve Bank, and says that, hey, I have losses, please bail me out. So the RBI is asking how many customers are defaulting. And this bank is basically saying that I have a lot of customers who defaulted, I'm not able to recover the loan. So RBI says, okay, fine, let me look into the numbers. And they come back saying that if you have less than 5% customers defaulting, then I'm not going to bail out them. But if your average is greater than 5%, then yes, okay, I'll help you. Right? So here, no action. Here, take action. Do something different, right? Take action. Right? So let us now move on. And yeah, before that, let me see if you have any questions. Anyone has questions? Please raise your questions, friends. Do we have any questions? Okay, I see no questions. All right, let me proceed in that case. I hope everybody is able to hear me. I see the poll that there are a few people who are saying I'm not able to. They are not able to hear me. All right, so let's move on. Now, whenever you are doing this kind of a statistical analysis, inferential statistics, right? You're trying to estimate a value. We need to see what is that value you're estimating. You're estimating, fine. But what is that you're estimating? We represent that as y. And this y can be either continuous or discrete. If you are familiar with data types, then you will understand that dealing with continuous data is a big problem, right? There are certain conditions that we need to look at, right, that the data satisfies. We say it as normal distribution conditions, right? The data should be normal without any abnormal conditions. So we need to verify those conditions. If it is discrete, then no problem. We can straight away deal with that discrete data. So based on what is the value that you're estimating, there are different hypothesis tests that you have to perform. Now in hypothesis testing, thanks to the tools R and Python, there are ready-made functions given to you. But the problem is you need to understand what test or what function you have to use in what conditions. That is the very important thing. Okay? So these flowcharts that you're seeing basically will give you an idea on what are the tests that you have to perform. Now this particular flowchart on the screen that you're seeing deals with a condition where the value that you're estimating is continuous in nature. All right. And we also have another flowchart. This is the second flowchart where I have a condition where the data is discrete in nature. Okay. We'll deal with this first. We will deal with a condition where your estimated value is continuous. Yeah, we always have to try the difficult things first. Okay. So we'll talk about this. Now, there are three different options or branches that you need to understand when the value that you are estimating is a continuous one. Right? So first understand the value, the data type of the value that you are estimating, and then see how many such values you are basically evaluating. Right? If you have a single value that needs to be evaluated, that means you are working with a single sample. But yeah, we are estimating for a population parameter. We say compare one population with an external standard. That means we have only one group or one population. In that case, we follow this flowchart. And here I have three different tests. 1, 2, 3. Not in any order. Okay? Not in order, 3 tests are there. Similarly, I have two populations, and here basically I'm comparing which is better. Whether the first option is better or the second option is better. Right? So in such cases, again I have 1, 2, 3, 4. 4 tests possible. And if you have greater than 2 cases, then we go with this branch, and here I have 1, 2, 3. 3 tests. So in total I have 3, 3, 6 plus 4, 10 tests covered here. This is not the exhausted list, but this is the flow chart generally that is followed. Right? And we also have different variations of the same tests as well. Different scientists came up with different tests. Okay, so let's look into an example and try to follow this flowchart and understand how the business problems are solved. All right. So I'm basically talking about one example here, fabric data. This is the example. The length of 25 samples of a fabric are taken at random. Mean and standard deviation from the historic 2-year study are 150 and 4 respectively. Test if the current mean is greater than the historic mean. Assume alpha to be 0.05. Alpha is the significance level. It's basically called as the chance of going wrong. As I recommended, go through the YouTube videos, try and understand these terminologies. What does alpha means, right? So at a high level, I'm saying it is a chance that you might go wrong when you are predicting, when you are estimating, right? You will be estimating the results with 95% confidence. That means there is still chance of 5% that you might go wrong. That is your alpha. So let us try and solve this problem now. The fabric manufacturing textile industry is there, and in that industry, the fabric is getting manufactured, right? And that fabric is sold to the clients based on the length that it is getting manufactured. So in meters, for example, you are selling it to your clients. And there is a machine which is basically cutting this particular fabric at an appropriate length. Now, historic 2-year study, that means your historic all these years, right, from 2 years back, what we have seen is that the mean is 150 meters The mean is 150 meters, and there is a small variation to this 150, which is given as a 4 meters. Standard deviation is 4 meters. So the machine is cutting on an average at 150 meters. But yeah, exactly it may not cut right every time. So that variation on an average is 4 meters. These are the standards which are given. Now, we need to verify whether the machine is cutting the fabric length in the appropriate sizes or not. This is a business condition. We have to verify that. We'll regularly keep checking, right? So we are checking it. So what we basically have to do is, we look into the fabric length that the machine is cutting and measure the length of that. I mean, record the length of the fabric and then see whether it is close to this, right, historic value. That's a standard, right? Now, if your machine is cutting the fabric which is less than 150, let's say it is cutting at 140 meters on an average, what happens? Right? Your client will come back to you saying that, hey, you have charged me for 150 meters, but you have given me only 140 meters. So brand value takes a hit. Your customers would be dissatisfied, but you have a workaround here. You can handle this problem saying that, hey, there is a problem in the machine. Let me compensate. So you're giving that, let's say the cost that they paid for 150 meters, right? For the 10 meters, whatever you have charged, you're going to return. Or you're going to give that 10 meters. So two options are there in this particular case. If your mean is less than 150, ideally it has to be what? Equal to 150, ideally. But it may be less than 150. In this case, you have workaround. Case 2, the mean is greater than 150. That means the machine is cutting, let's say, 160 meters. The fabric is being cut at 160 meters. Now what happens? Will your client come back saying that, hey, you have given me 10 meters extra, please take the cloth back? Or would he say that, okay, you have given me extra, take the money? Your clients will never say that, right? In fact, they assume that you are giving that additional cloth for free. Now here, the problem that you would have is losses. You would accrue the losses, right? So if this is the condition, if this is the scenario, then you have to halt the production, stop the production, and see what is the problem in the machine, rectify it so that it doesn't, right, cut the length in greater than 150 meters. So scenario, the entire business scenario is explained here. Now we need to basically come up with business problem statement, okay? And then we need to follow the flow chart and understand what we have to do now. Okay? So let me take a Word document and I'm recording this, okay? So case study 1. Let me do this, increase the font size. Case study 1, we say fabric data. So the first statement, business problem. Verify if the length of the fabric is being cut at appropriate sizes or lengths, right? So that you can take an action. Should I continue the business or should I stop the production to do a maintenance task? Then we need to collect the data. So I will show you the data. Okay. So I'm launching R and I'm reading the data set. In order to read the data set, I'll say read R. Read this data. And here I will have fabric data. Now what we have done is we have randomly selected 25 fabrics. The machine cut the fabrics, right? So randomly we have chosen 25 samples, right? And recorded the lengths. And this is your data. So how many populations do we have, or how many groups we have? A single group, right? A single parameter that we are having here. So if I go back to my screen here, it is length, fabric length, right? Yeah. Y is the output that we are estimating is fabric length. Length is continuous data. And the populations that we have, the parameter that we are looking at, is a single population. Right? So X is discrete, which is single population. So we come to this particular branch. We are trying to compare the population mean, the current mean, with external standard. That external standard is the 2-year study, 150 meters. Okay, this is what we have to do now. Right? So we have collected the data. You might say that, why don't we do average? Right? A lot of people might say that we have collected the sample data, right? I have 25 records. Simply do average. Wonderful. Very easy, right? In R, we do mean of this data and you get some result. Okay, let me do that. Let me, in fact, do it and show. So I have fabric length. Let me do this here. Mean of fabric dollar column. So my current mean, which is represented as X bar, is 155.064. Now, if I take that external standard, this external standard is 150 meters. So we can say here that this mean is greater than this. So you can make conclusions here. You can say that the current mean is greater than 150. So stop the production and verify. But remember, it is based on 25 sample lengths. What if there is another study which is performed by another employee, another data scientist, who is also recording 25 samples or 30 samples, whatever that is. Okay, this is sample 2. This is sample 1. Do you think for that employee, when he has taken another set of 25 samples, would he get the same result? He might get only 140. The sample varies, the calculation varies. So now based on this, what conclusion can I make? I cannot generalize for the entire production, right? This is the reason why we don't just take mean, sample mean and conclude. No, because samples might change. We need to estimate this result based on multiple samples. Estimate mu based on these samples. If I can get the population estimated value, using this, I can compare with the external standard and then I can conclude. Right? So let us try and do that. But in order to do this study, we need to look at various conditions. So I identified what is the flowchart that we need to follow. And we've seen that the data that we are trying to estimate, the parameter that we are trying to estimate is continuous, right? If this is continuous, then we need to verify whether this is normally distributed or not. Is this data normally distributed? Is it normal, or do we have any abnormalities in the data? Right? So that is the test that we need to do. We are verifying, is the data normal or not? Okay. So let me go there. And what is the test, or how can I validate whether the data is normal or not? If I have to verify whether the data is normal or not, then we have already learned that there is something called as normal QQ plot. Normal QQ plot. Right? And this normal QQ plot will take the standard Z values on x-axis and the sample data on y-axis. And then compares the sample data with Z values, which is standard normal data. And if my data falls on the straight line, then we say it is normally distributed because the distribution of sample data is similar to Z distribution. But if it is like a curve shaped, either it is like this or like this or like this or like this, any curve shaped or non-linear, then we say the data is not normal. It does not follow the distribution of Z. So let me quickly verify, show you that. Okay. So we'll do QQ norm. And what is my data? Fabric $fabric. And to verify here, I also have QQ line. And this is your QQ norm. Now visualization, we are looking at the plot, and what can I say? It's really ambiguity, right? Few people might say it is normal, few people might say it is not normal. There are only 25 records. So it's a little tricky condition, especially when we have visualizations. These kind of conditions, right? These kind of scenarios would come. So what we are doing now here is, we have to quantify it. We have to mathematically use certain tests and measure that normality. And there are different tests that we can follow here, different tests that can be followed. And what I am doing here is an Anderson-Darling test. Anderson-Darling is one of the tests, or one of the scientists who came up with a test to prove that data is normally distributed. So in order to do that, I use this library called non-test. Install the package and load it. If it is already not present, install it first. Now, what does this normality test do? Okay, I don't have this package documentation ready. My system has a challenge, so it will not give me the details of few of the packages. So I'll check in the Google. You can try with question mark. If it doesn't come, then you can come here. Package not test, it is basically used for testing for normality. Right? 5 omnibus tests for testing the composite hypothesis of normality. AD test, CVM test, Lilly test, Pearson test, SF test. So AD test is what I'm trying. You can now probably explore the different options which is given here, right? CVM test, Karma-von-Mises test for normality. Then we have Lilly test. This is also known as Kolmogorov-Smirnov test. We also have another test called as Pearson chi-square test. Then we also basically have Shapiro-Francia test, Franca test basically. So these are the 5 tests that we have in the normality test package. And I'm doing the first one, okay? You can try with other tests. Anderson-Darling test. I'll say AD.test and your data. But before I do this, I want to make assumptions. So let me document that. We have collected the data. Y is fabric length, which is continuous in nature. And we have 25 lengths collected at single sample. And because it is continuous data, I'm doing normality test, normality verification. Now, in the normality test, I'm doing a test, right? In the normality test, what would be the assumption here? We are doing hypothesis testing. Any test, right? We make assumptions and then try to prove it. So, normality test that we are considering now for the continuous data, the default assumption would always be that the data are normal. If the data is continuous, the data type of the taken sample data is continuous, then we say that the record that we have collected for that sample, they follow normal distribution. That's the default assumption. And we have to prove that, yeah, it is normal or not normal. Basically, the data are normal or not normal. So, alternate for your null hypothesis here is that data are not normal. And to prove this, we have A/B test. Okay. Now, we take this and execute it, just execute it, and we look at the statistic value which gives us this p-value. Okay? So we are interested in p-value only. Now what is this p-value? Right? We'll try and understand that. So if you remember, or please try and go through the study. We are trying to see the data is normally distributed. So this is the standard bell curve. Assume it is a standard bell curve. We call it as standard normal distribution, which is represented as Z. Okay, and Z always has 0 and 1 as the parameters, mean and standard deviation. This is basically standard, but anyways, we are talking about a continuous data. And for continuous data, this is how your distribution looks like. And we are saying that I have confidence, right, that the data is not, the data that we are taking are normal. And industrial standard says 95% is the confidence which we by default take. The entire area under the curve basically is minus infinity to plus infinity. Okay, everything falls under this, isn't it? So we are drawing this limits. Okay, assume it is symmetric. We are drawing these limits and saying that 95% of the times I'm right treating that the data will fall here, which is accepted. This is accepted data. Okay, so if my value falls between this, then I'm gonna accept, and this area outside the 95% thing that we're drawing is something which is not accepted. So we're saying this is region which is not accepted. So here we represent this as 1 minus alpha, and this is alpha. The blue shaded portion is alpha, and this is symmetric in nature. Remember, the bell curve is symmetric in nature. So this becomes alpha by 2, this becomes alpha by 2. So we are saying that the result at 95% of the times would fall in this region, which is represented as 1 minus alpha. But if the value is not falling in that, then it is not accepted. It could be lower than this value or greater than this value. Okay? Then we don't accept. So we basically get a statistic calculation. When we are doing these mathematical calculation, you will get some value. And Anderson-Darling test is also getting some statistical value. Using that value, we try to see what is the probability area under this curve. That is your p-value. For a given statistic, value, what is the area that it covers? Towards the left side portion, okay? Now, if that value that we are getting is less than alpha, if it is less than alpha, this value, whatever you're giving, is either equal to or less than alpha, that means the value is falling in this accepted region. You are not falling in this particular region where it is rejected, right? But if my p-value is greater than alpha, then you are saying the chance of going wrong is more. The value that you are getting is falling in this region, but you see you are covering that and then, right, saying yes, the result is falling somewhere in this alpha portion. So you're basically seeing whether the result will fall here or in this portions, left curve or left tail or right tail. And this p-value is read as the chance of going wrong if you take action. If action is taken. Hypothesis testing, we are assuming that whatever we are doing is good, but we need to find an evidence, right? So we do a mock, let's say we do a pilot launch and we do a test. And we are generalizing the results based on that sample test, right? So that for generalization, we take this p-value. If you take an action, what is the chance that the results are falling in this unaccepted region or accepted region, right? And industrial standard, alpha is set as 5%. It means you can go wrong by maximum 5%, not more than that. When you are estimating, there may be a mistake, right? There might be some chance of going wrong. So industry understands that you're not a god, right? Statistics understands that we're not god and we cannot estimate with 100% accuracy. So we have an industrial standard of 5% chance. Now we are verifying whether the chance that we are getting when we are doing the action is within the limit of accepted value or is it beyond this accepted value, right? These conditions. And if it is less than the accepted value, then we take action. You can go ahead and take action, right? But if your value that you are getting is greater than alpha, the chance of you going wrong is more than alpha, then you better don't take action. P-value is greater than this alpha. So your confidence region is less now. If this increases, let's say this is increasing, then your confidence portion is reducing, right? Isn't it? So you better do not take action. This is what we interpret from the p-value. There are different ways to explain this. But yeah, this is one of the easiest ways that I feel to consider this p-values, or we absorb the p-values. So p-value is nothing but chance of going wrong. And we compare this with standard, industrial standard, which is nothing but alpha. It is represented as alpha, which is 5%. Now, if the p-value that you are getting, when I compare, if it is higher than alpha. That means p-value is greater than alpha. That means p-value is higher than alpha. P high. In this case, what should we do? We better go with null hypothesis. Risk is more, chance of going wrong is more. So no action. You better don't take action. So we say P high. We say P high, null fly. Null fly. Null means null hypothesis. Fly means accept it. Go with null hypothesis. P high, null high. Null fly. But if you see that the p value that you are getting is lower than alpha, that means if p value is less than alpha, then the risk is less, right? If you take an action, the chance of you going wrong is less. So it is accepted. So that means you better take action. Do something different. Go ahead. Take risks. So P low, then we say null go, which basically says reject null hypothesis. So these are the two statements that we need to by heart remember, and it makes easy, right? It makes our life easy to decide on what should be considered with respect to the p-values. And in hypothesis testing, we are only worried about this. Remember, we are not statisticians, right? So let's not worry about the statistical calculations. We have to understand the business problems, the business conditions, and then we need to just understand what test needs to be applied, and then the results have to be interpreted with respect to the p-value and map them back to the business conditions. Right? So let me see if you have any questions. Alicia, yes, these are already available on the LMS, in-house LMS that we have, right? And anyways, YouTube videos are there. So probably let me see how I can basically share those flowcharts. Difference between confusion matrix versus hypothesis table. They are interpreted in a similar lines, Adirathi. They are similar, though the interpretations are completely different, but the conditions, 2 by 2 conditions, right? That's a 2 by 2 matrix. The conditions can be interpreted with similar examples. Okay, Hari, will the default assumption can vary based on the survey or with multiple theories? See, for any business problem, Hari, if you are clearly understanding the business problem, then you'll always see that there is one business, your current condition, right? There is only one current condition. Yeah. Next. Any other questions? The screen is maximized already, right? You're not able to see that? Okay, that's strange. Okay, yeah. All right, so let us proceed further with the discussion. Yeah. So we are doing an Anderson-Darling test and we get p-value. So let me record this p-value. I will copy this and record it into my documentation. So p-value I got is 0.2055. And remember, this p-value has to be compared with alpha. And that alpha basically is industrial standard. Alpha is 5%. Industrial standard is 5%. So we compare with alpha, and when I do that comparison, this p-value is greater than that alpha, right? So let us record this. We'll say p high null fly, which basically implies we fail to reject null hypothesis. We don't have evidence to reject null hypothesis. Yeah, that's what we see. That means we have to go with our default condition. And what does our default condition say? Data are normal. So we are proving that data are normal. So let us go back to the flowchart. So we are seeing this condition where data is normal or data are normal. So we follow this. Now remember what we are trying to do here. We are trying to check the current mean of the fabric length is cutting, or the machine is cutting the length of that fabric appropriately to the standard. So we are verifying whether the current mean is close to 150. If my data are normal, then I have certain conditions where I say mean is equals to median is equals to mode, the area under the curve is 1, right? All those conditions, the normal distribution properties would hold good. And I can consider mean as is. But if my data is not normal, if my data points that I have are not normal, then the solution that I have to apply first is to try and make the data normal. I don't want to work with abnormalities. I want to consider the data to be always normal. That is something that we'll assume, right? Because all the statisticians who came up with these logics, they assumed, excuse me, they assumed that the data are always normal. The world is normal. So remember this. If you are assuming that data are abnormal, that abnormalities could be anything. We don't know, right? And we cannot define the pattern for that abnormalities. So there are not too many logics which are predefined for abnormal data. Hence, we try to make this non-normal data to normal. And to apply that, or to do that, we do transformations. We apply transformations. Transformations basically is a mathematical application on the sample data wherein your magnitude of the data gets altered. So we are, another definition basically, to put it in a simple words, is transformation techniques are the techniques wherein we are manipulating the magnitude of the data that we collected. The scale of the data is getting manipulated. This basically alters the distribution of the data. And we try experimenting on altering the data in different ways, the magnitude of the data in different ways, and see which technique or which alteration or which scale might give us the distribution to follow normal properties. That's the transformation techniques. So we experiment. Now you might say that, yeah, I tried. Hey Sharath, you are explaining all this, very good. I did try transforming the data, but none of them actually worked. I tried with all the transformations that I know, but none of them worked. Then what should I do? In such cases, we proceed with non-normal test cases. We can also call it as non-parametric test cases. Let me erase this and rewrite it. Non-normal test cases. or non-parametric. Non-parametric test cases. And when you have a single population, then the test that you can perform, the non-normal or non-parametric test case that we apply is called as one sample sign test. Yeah, that's the name. And if your data is not normal, in that case, mean is not equal to median. This is your property of normal conditions, right? So you're having an outliers. You have abnormalities in the data, so which is definitely affecting your mean. So mean is not equal to median. And when you have a value, an outlier or an extreme value, which influences mean, then we don't take mean. We consider median. So in non-parametric test cases, we consider medians. So the business objective that I'm trying to solve would say median, is it appropriate to 150 meters or not? Median of the data. Okay, that is the difference. Right? So everything remains same except for considering median over mean. Okay, that is a simple way to understand the non-parametric test cases. Alright. That's about this. Now, in our data set, we found that the data is normal. So we are proceeding to the next question. Population standard deviation is known or not? Do we know the population standard deviation or not? And in our business problem, it is clearly given, right? It's clearly given the population standard deviation. These are considered as standard for 2-year studies, so we are generalizing it, right? So your mean 150 is population mean, and standard deviation 4 meters is your basically your population standard deviation, sigma. Population standard deviation, yes, it is known and it is equal to 4. So sigma is equal to 4 meters, which is given. If it is given, then we follow this particular test. The test is called as one sample Z test. If sigma is not known, then we apply one sample T test. Ultimately, we are trying to calculate the mean of population. Right? We want mean of the population. But what we are doing, we are taking 25 records and we are calculating sample mean. And given this point estimate, if I have to estimate mu, then we use confidence interval formula. And confidence interval formula, there are two approaches or two formulas. When sigma is known and when sigma is not known. These are the two conditions that are two formula that we know. If sigma is known, then we go with this condition. Point estimate plus or minus Z into standard error, the Z value at 1 minus alpha. If sigma is not known, then my confidence interval says point estimate plus or minus T. Student T distribution is considered at 1 minus alpha into n minus 1 into standard error. And standard error here, because I know sigma, it will be sigma by square root of n. And here, the standard error, because I don't know sigma, I will take small s, by square root of 5. To capture the variations that may occur if I take sample standard deviation are captured using t-distribution. Right? So these are the two differences. Hence we call it as z-test, we call it as t-test. So if you look at this, if population standard deviation sigma is known, we go with z-test. If it is not known, then we go with the t-test. Right? And the rest of the calculations follow the same sequence. Calculate mean, which is point estimate. Using this point estimate, you have to calculate parameter. And to do that, we have confidence interval, and we have two options in the confidence interval formula calculations based on your z or sigma value, which is known. Right? So let us try and apply this. But remember, we are trying to solve a business problem here. And to decide what test we need to apply, we followed all these steps. So we are doing one sample, z testing. And using this one sample z-test, we need to solve the business problem. Now, what is the business problem here? The business problem says, verify the length of the fabric and decide whether you need to continue doing the production or halting the production. Right? When would you continue the production? When the current mean is less than or equal to standard, which is 150 meters. We discussed, remember, ultimately we need 150 meters as the current mean, but even if it is less, no problem, because we are going to compensate the customer. So I don't want to take action, no action. But if the current mean is greater than external standard 150, then we say take action. But in hypothesis testing, we have the challenge where you cannot do comparison of two operators in a single execution. You cannot do that. Mathematically, it cannot be done. Basically, you're verifying, right? Hence, we split this into two options. So I'll take case 1. I always try to make it simple, right? So what I'll do is, I'll say current mean is equal to standard mean, which is 150. Then yes, no action. This is what we want. So verifying whether it is equal to or not equal to. This is what we are verifying. So your null hypothesis says mean is equal to standard mean. And here I say mean is not equal to standard mean. Here, yes, I need to take action to find out which is, right, basically the mean is not equal, right? So which is greater? So first we'll verify this, because I can, ultimately I need to verify whether it is equal or not, right? So first condition is this, I'm checking this. And the test that I'm using is called as z-test. And for getting the z-test, we do teaching demos. This is the library that we do. So install and import that, and you can say z.test. It says z-test for known population standard deviation. Sigma is known for us, right? So this is the syntax. Case 1, wherein I have decided the hypothesis is equal to, not equal to. So what I'm basically saying is, I'm drawing this bell curve. and I'm saying this is 95%, assume. I'm saying whether it falls here or does not fall here. When I say does not fall here, it might fall here or it might fall here. Right? The mean, current mean might fall here or fall here. You're basically verifying whether it is here or not. So alternatively, if your null hypothesis says it is falling here, then alternative could be either this side or this side. So I'm saying alternative is two-sided test. Two-sided. It could be this side or this side. The number of samples I have is 25. Standard deviation is given as 4. Standard mean is given as 150. And this is your 25 records. Data is passed. And the confidence interval by default is 95%. These are the basic parameters that we need to pass for the test. And this test is giving us a z-statistic, and using that z-statistics, we calculate this p-value. What does this p-value say? 2 into 452 into 10 power minus 10. This basically is equal to 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 4, 5. Now, this is your p-value. Is this p-value greater than alpha or less than alpha? Where alpha is 5%. Right? That's what we have to consider. So internally, it is calculating the mean. This is your point estimate. Using this point estimate, it calculates confidence interval at 95%. So this is what you're getting. So your confidence interval in the diagram 153.496 and 156.632. Right? This is your confidence interval, and we are verifying whether this interval will have 150 or not. Is that interval has 150? It doesn't have, right? So your alternative hypothesis is being correct here. So P low, null go. So if I have to go with that standard, I'm in that conditions. The P value that you are getting is equal to 0.00000. How many zeros I have? 3, 6, 7, 8, 9, 2, 4, 5, and this is less than 0.05. And if this is the condition, we say P low null, which basically means reject null hypothesis. An alternate hypothesis says means are not equal. So we go with case 2. We need to understand which is greater. Right? Case 2, which is greater. Whether it is less than or greater than. So null hypothesis, no action condition. Say if the current mean is less than standard mean, then we take no action. We have condition, or we have an alternative where we can compensate the customers. Whereas alternative hypothesis says if current mean from the 25 samples that we have taken and estimating for population, right? So if on an average the current mean greater than, then you say yes. What is that action? We'll come here, and if you observe, the alternative hypothesis is saying this is your 95% confidence, and you're saying null hypothesis is less than 150. The interval that you're getting, you say, right, this interval will be less than 150. You're saying current mean is less than standard, right? Which is 150. So this interval values that you have are less than 150. That means you're saying your null hypothesis or your 150 is falling somewhere here. Right? That's what you are basically saying. Greater than 150. Or you can say these values are less than 150. Okay. Now for alternative hypothesis, you're saying current mean is greater than standard 150. That means this interval that you're getting is greater than 150. That means your 150 is lying in this blue portion. Right? So you're saying alternative, the result that we are getting is greater. Okay? Two-sided means the mu can be this side or this side. But the second test that I'm doing is I'm checking that the result is greater than alpha. That means it is falling here. We are verifying everything else remains same. The parameters for the z test, everything else remains same. Only this changes. When I execute this, I get again the p-value. And look at this. Your estimated value, 95% confidence interval, is calculating the lower window and ignoring the upper limit. You are only verifying whether the lower limit is less than or not. This is your current mean, point estimate. And the confidence interval that you get will have lower limit and upper limit. I'm seeing whether your mu is falling this side or this side. And alternative hypothesis is this. You are saying this, right? So it is verifying only for this. So lower limit is calculated and seeing whether this is less than this value or greater than that value. So we found that 150 is less than this. The current mean is greater than 150. Right? So the p-value that you are getting is this. So let us record this. Let me just copy this. Rather than typing so many zeros, we'll just copy it. And this is definitely less than 0.05. So what is the statement? P low, null low, right? So that means you go with alternative hypothesis, which is current mean is greater than the standard mean. Is 1. So this basically tells us to take a conclusion. Take action. What action? Stop the production and verify the problem with the So we have successfully concluded a business action. Right? Yeah. Any questions on this now? Let me take your questions, friends. Anyone has any questions? No questions? That basically means I have explained the concept very well. Is that a fact? Oh, okay. All right. So inferential statistics, let me summarize everything. So inferential statistics works on sample data, but we have to make inferences about population. And here we also have to learn about how do we draw samples and all that. That's a different study. Probably we'll do a different webinar for that. And once you have the sample data, we do inferences by using these tests. And these hypothesis tests can be classified into two types: parametric, non-parametric. And always null hypothesis is the no action scenario, default condition. And then we also have to come up with an alternate option. That's called as alternate hypothesis. And the tests that we are doing have to be done at a certain confidence level, which is given as 1 minus alpha. Industrial standard is 95%. This is where your value should lie. Right? The results that you are getting should lie in this region. But it might also be a scenario where you might make a mistake. Type 1 error, which says, though your current condition is the right thing to do, you are going ahead and doing something different. That is type 1 error. Then type 2 error is also something which might arise, which basically says you need to do something different, but you are not doing that, not taking action. So we classify this type 1 error as alpha error, type 2 error as beta error. And we also have beta, 1 minus beta, which is called as power, which is the right thing to do when you should take action, which is known as power of the test. And in hypothesis testing, you have multiple scenarios which are broadly classified first as the value that you are estimating is whether continuous or discrete. If it is continuous, then we always check whether the data is normally distributed or not. If it is normally distributed, then we go with normal test cases. If the data is not normal, we first try to make it normal. If it is not becoming normal, then we go with non-parametric test cases, non-normal test cases. And if I know sigma, then to estimate the population parameter, I would use z-test. But if I don't know sigma, then I would go with e-test. And using the z-test and t-test, I get the statistic value. Using that statistic value, I calculate the probability of whether the result is falling in the accepted region or not. If it falls in the accepted region, then go with your regular default action. But if it is not falling in that accepted region, if your p-value is less, then you have a better chance, right, or less risk to go ahead and take action, right? If you do action, the chance of you going wrong is less. And like that, likewise, we have multiple test cases. Tomorrow we will be discussing about paid t-test, and probably I'll explain about a norm test case as well. The difference between Anova and norm. Of course, that is also detailed discussion would be there in one of the webinars. But I will explain when to go with a norm and when to go with Anova, along with one example for paid t-test. All right. So let me see if we have any questions one more time. Yes, friends, please come up with your questions if you have any. All right, friends, if no questions, then I think we can wrap up the session for the day. More interesting things coming up tomorrow. Let's connect again tomorrow at same time, 8 a.m. IST, Indian Standard Times. Thank you so much. Take care and be safe.